Okay, welcome to lecture 32. So we are starting Unit 5 today. Okay, and Unit 5 is something called plane autonomous systems. And in fact, we've already seen an example of a plane autonomous system in lecture 31 from Unit 4. Well, a lot of this stuff will be revision and a fairly slow introduction, I guess, or a fairly tame introduction. So what we're going to discuss, what is an autonomous system? We're going to discuss dynamical systems, phase, planes, trajectories, drawing a phase portrait, which we've already done a little bit of, properties of trajectories, and critical points of autonomous systems. So let's get into it. So if we have a system of n first order ODEs, they don't have to be linear, they can be non-linear. But the point is that they're all ODEs, they all have the same independent variable t, and the right hand side of each of them, each of the equations, only depends on the dependent variable. It does not depend on t at all. T is the independent variable. The right hand side of these equations do not depend on the independent variable at all. Okay, so we call this system an autonomous system because the right hand side of each equations are independent explicitly of the variable t. Of course, x1, x2 through to xn change as t changes, so they're implicitly a function of t, but t doesn't explicitly appear on the right hand side of that equation. Okay, when the independent variable is time, so if t represents time, then we call this system a dynamical system because something is changing dynamically in time. Okay, so that word dynamical system is a commonly used in mathematics and physics. Okay, and the solution x of t, so recall if we write this system in matrix form, the solution to that matrix form, or the solution vector, is called x of t, and we made the x bold to say that it's a vector. We call that solution the state or the response of the system. Okay, so now when n equals 2, or in other words we have only two equations, so dx by dt equals some function of f, dy by dt equals some function of g, we call this a plane autonomous system. Okay, so x and y are dependent variables and t is the independent variables. And just like we learned in lecture 31, the xy plane we call, in this plane autonomous system with n equals 2, where we have two ODEs, we call this xy plane the phase plane. Okay, and so again, as we discussed in lecture 31, the set of points x of t, y of t in the xy plane, sometimes people call it the graph of the solution, is called a trajectory of the system. And so in the last lecture, we plotted some trajectories of a system. But we also introduced the orientation on a trajectory, which is just the arrow on the trajectory indicating the direction of increasing time, or increasing t. So again, this is all stuff that we did in the lecture 31. So we're just reminding ourselves, and we're going to advance that a little bit now. So let's look at an example of a plane autonomous system here. Dx by dt equals x, dy by dt equals negative y, plus we have some initial condition when t equals 0, x equals x naught, or when y equals 0, y equals y naught. And so now these ODEs actually are not coupled together. So for example, in the first equation here, dx by dt, there is no y that appears on the right hand side, so in fact I can solve this equation independently of what y is doing, and similarly I can solve dy by dt independently of what x is doing, just using separation of variables. So I'll leave it to you to show that the solution for x of t is x naught times e to the t, the exponential of t, and the solution for y is y naught times the exponential of minus t. Okay, so we're going to look at a few cases here. If the few cases of where the initial condition, right? So if the initial condition x naught is equal to 0, y naught is equal to 0. Okay, then the initial condition just enters into our solutions here, then it's pretty clear to see that x of t equals 0 and y of t equals 0 for all time. Okay, so if we start at the point 0, 0, then we reach an equilibrium state where we don't move off that state at all. X does not increase, y does not increase, because if x naught equals 0, x of t, x in time, is 0 all the time for any value of t. And similarly, if y naught equals 0, y of t is equal to 0 regardless of the value of t. Okay, so in other words, we get a point in the middle of the graph here that does not move. Okay, what about case 2, when if x naught equals 0 but y naught is not equal to 0? Well, if you think about that, x naught equals 0 still means that x is 0, so we always stay on the y-axis here. Y of t, if y of t is not equal to 0, as t increases, e to the t moves to 0, right? So we know that the limiting value of y, when x naught equals 0, the limiting value is going to be 0 as time goes to infinity. Okay. Okay, so now if y naught, the initial condition on y, is greater than 0, then we approach y naught e to the minus t. This goes to 0 as t goes to infinity, right? So if our initial condition is y naught greater than 0, x is still equal to 0, so we're on this vertical line here. But as t goes to infinity, y naught e to the minus t approaches the origin, or approaches 0. And in fact, it's exactly the same if y naught is less than 0. So if we start on the y-axis below with negative y, so y naught is negative, as t goes to infinity, this is still going to 0, right? As t goes to infinity. So we're still approaching this origin 0, 0 if we start on the y-axis. Okay, well, what about the case when x naught is not equal to 0, but y naught is equal to 0? Well, again, if y naught is 0, then y of t is always going to be 0, so we're always going to stay on the x-axis here. But if x naught is not equal to 0, you can see we're going to approach some kind of infinity here, because as t goes to infinity, e to the t is going to infinity. So if x naught is greater than 0, x naught e to the t is going to go to infinity as t goes to infinity. So if we start at this point here on the x-axis, y naught is 0, so y is always 0, we stay on this axis. If x naught is positive, we move off to positive infinity. If x naught is negative though, well, e to the t is always positive, right? It goes towards a positive infinity as t gets larger, but for no value of t does it ever get negative. But if x naught is negative, then actually as t goes to infinity, we approach negative infinity. Okay, so if we start in the negative x, on the negative x-axis here, as t approaches infinity, or as t marches on, we move towards the left here, so we move this direction. Okay, well, what if now none of them are 0, but the initial condition we're given is x naught is greater than 0, y naught is greater than 0. Okay, so we're in that first quadrant here, where the initial condition is starting somewhere in the first quadrant. Okay, well then, by our two solutions here, none of them are 0, so they're just given displayed there. But I can actually rearrange this equation to make e to the t the subject to the formula. Okay, so if I multiply both sides by e to the t, and I divide through by y of t, then I get e of t equals y naught divided by y of t. Right, just rearranging that equation there, nothing tricky. But what it means is that this e to the t, exponential of t, I can substitute in the x equation. Instead of writing e to the t, exponential of t, I can write y naught divided by y of t. So therefore I can write x of t, the solution of x is equal to x naught over y naught divided by y of t for all t. Okay, so if I multiply both sides of that equation by y of t, I get x of t times y of t as a constant, which is just a hyperbola. If you remember your geometry from high school or from first year mathematics, this equation, x times y equals a constant, is just a hyperbola. Okay, well, again, if we say, well, x naught and y naught are both greater than 0, as t goes to infinity, x is still going to infinity, right? So as t goes to infinity, x is going to infinity, and similarly, if y naught is greater than 0, as t goes to infinity, e to the minus t is going to 0, so y is going to 0 as t goes to infinity. Okay, so we can take these two relations here, knowing that we've got a hyperbola solution, and we can plot that. So in the first quadrant, if we take the initial condition in the first quadrant, x naught and y naught are greater than 0, so if we take some point in the first quadrant, then we get some kind of hyperbola solution where y is going to 0 as t goes to infinity. So see here, y is reducing closer down to the y equals 0 line, and x is going to infinity as t goes to infinity. Okay, well, we can do play the same thing for now x naught greater than 0, y naught less than 0, x naught less than 0, y naught greater than 0, or both of them greater than 0. So if we look in all four of these quadrants, we always find that x of t times y of t is a constant. So in all four of those quadrants, we are going to get hyperbolas, okay? So let's just discuss each of these cases one by one. In the case x naught greater than 0, y naught less than 0, so this is the bottom right quadrant, the fourth quadrant. As t goes to infinity, x naught is still going to go to infinity because x naught is positive. Sorry, as t goes to infinity, x goes to infinity because x naught is positive, so we get something positive times something that's positive going to infinity. Y naught is still is negative, but y is always going to go to 0 as t goes to infinity because e to the minus t goes to 0 as t goes to infinity, regardless of what y naught is doing. So if we plot a point in the fourth quadrant here, we know that it's going to be it's following a hyperbola shape, and it's going to x equals positive infinity and y equals 0. Similarly, if we look in the x less than 0, y greater than 0, so the second quadrant, the upper left up here, again, x naught here is negative, so as t goes to infinity, x is going to go to negative infinity. And similarly for y, as t goes to infinity, y is still going to go to 0. So if we take a point in the upper left quadrant, we follow this hyperbola path down as x goes to negative infinity and y goes to 0. And then similarly in the third quadrant, x goes to negative infinity and y goes to 0 as t goes to infinity. Okay. So we have a hyperbola plot like so. So we can plot all these trajectories on the system to create our phase portrait, and we get something like this. So again, along the y-axis we get two arrows that are pointing towards the origin. Along the x-axis we get two arrows that are pointing away from the origin. And we get these hyperbola solutions in the other quadrants. Okay. So this is the phase plane for this fairly simple system here, autonomous system. Note that the equilibrium state at 0, 0, so that point where we don't move at all, that is equal to 0, 0. That is a saddle point because some trajectories converge to the point while others are repelled away from the point. Okay, and what we're going to do in this unit is well, find out what kind of equilibrium points we can have there. Okay, but first I just wanted to introduce some properties of trajectories that can be found in autonomous systems. So there is a trajectory through every point in the xy plane. So no matter what initial conditions we chose on that previous example, there was a trajectory that passed through that point. So in other words, regardless of your initial condition, you start on a trajectory and you carry along following that trajectory. Okay, but a trajectory cannot cross itself. Okay, so you can't have a trajectory that intersects itself. So this is not a trajectory of an autonomous system, because you can see here, if we start at this point up here, we travel around here, and then travel up here, and then, oh no, we intersect ourselves. We intersect ourselves here. So this cannot be a trajectory of an autonomous system. However, the only time we might be able to intersect ourselves is if we have closed curves. Okay, so closed trajectories represent periodic solutions. So here we have an oval here, which is a periodic solution. This can be a trajectory. So even though if we start at this point here and we travel all the way around and we intersect the starting point, well, we're still on the same curve. So in fact, this closed curve can be a trajectory. And in an autonomous system, these closed trajectories represent periodic solutions. Okay, so recall in that previous example, at 0, 0 was what we were calling an equilibrium point. But another name for these points are critical points. And so a point x0, y0 is a point where the function f of x0, y0 equals 0 and g of x0, y0 equals 0, where f is the right-hand side of x, the differential equation for x, and g is the right-hand side of the differential equation for y. Okay, so if we find a point x0, y0 such that both f and g are 0, okay, if you find a point where f is 0 but g is not, that is not a critical point. Both of these functions, f and g, have to be equal to 0 for the same point. Okay, so if you find a point where f and g are both equal to 0, that is called a critical point of the system. Okay, the corresponding constant solution, xt equals x0 and yt equals y0, is called an equilibrium solution. Okay, so these critical points have equilibrium solution. If you're at these critical points, you do not move from this critical point, you stay still. You are stuck at that critical point. You cannot escape. So as an example, let's have a look at a system of nonlinear autonomous ODEs here. So autonomous because there's no t dependence. The right hand side depends only on x and y, which are the dependent variables. So, but again, this is a nonlinear system because I'm multiplying x by y, and of course I've got a y cubed, so that's obviously nonlinear. We want to find the critical points of the system, so all of the critical points, in fact. So, okay, what do we have to do to do that? Well, we have to say the right-hand side of these equations, 1 minus x times y, has to be equal to 0, and at the same time, x minus y cubed has to be equal to 0. So we have to solve this nonlinear system. 1 minus xy equals 0, x minus y cubed equals 0. These two things have to be true at the same time. Okay, so from 2 here, the second equation here, we can rearrange that and say, well, if I take y cubed to the other side, that's going to be x equals y cubed. Okay, so x has to be equal to y cubed. If now I use that relation in equation 1, so I get 1 minus x, y here equals 0, x I can change out for y cubed. So I get 1 minus y cubed times y equals 0. So 1 minus y to the power of 4 equals 0. Or again, I can rearrange this equation. I can add y to the power of 4 to both sides, and I get y to the power of 4 equals 1. Okay? And y to the power of 4 equals 1 has two solutions. y1 equals 1, and y2 equals negative 1. Well, okay, it has two real solutions. It of course has some imaginary solutions too, but let's not worry about those. Okay, so two real solutions, y equals 1 and y equals negative 1. Okay, well, if x equals y cubed, x1 is equal to y1 cubed. So y1 was 1, so 1 cubed is 1. So the point y1 equals 1, x1 equals 1 is a critical point. x2 equals y2 cubed, which is negative 1 to the power of 3, which is equal to negative 1. So negative 1 is a critical point. So at this point 1, 1, both of these, the right hand side of these differential equations is equal to 0. And at the point, also at the point negative 1, the right hand side of these is equal to 0. Notice what is not a critical point though is 0, 0. So the second equation, dy by dt, if x equals 0 and y equals 0, then dy by dt is equal to 0. Okay, but dx by dt would be 1 minus 0, 1. So that is not equal to 0. So at 0, 0, the second equation equals 0, but the first does not. So that is not a critical point. So that's a very important distinction, that both of these equations have to be 0 at the same time. Okay, thank you very much. In the next lecture we'll talk about what kind of behavior these critical points can have, and we'll start classifying those critical points. But the most important thing from this lecture is to know how to find critical points of a 2x2 plane autonomous system.